All right, and welcome to a sustainable business case for commercial air-to-water heat pumps presented by Mitsubishi Electric Sales Canada. And specifically, Chris DesRoches, a professional engineer and holds a bachelor's degree in mechanical engineering from Dalhousie University in Halifax, Nova Scotia. As an applied product manager, Chris is a subject matter expert on hydronic heat pump solutions. And you've probably seen him before. He's a regular host of these webinars and knows what he's talking about. So, Chris, welcome again.
Thanks, Matthew. I appreciate the introduction, and I'm glad you think I'm knowledgeable in these heat pumps.
I'm just reading off the page, but I know I've seen your webinars before, and you're very knowledgeable, so people should be in for a good one. Before you start in, just a reminder, we do take questions if you'd like. You can pop them in the Q&A button on the bottom of your screen or the webinar chat. But other than that, I'm going to go dark and let Chris do his thing. Thank you so much.
Perfect. Thanks, Matthew. So welcome, everyone. Thanks for taking the time to join us today to talk about air-to-water heat pumps. So I'm not sure if some of you attending today have seen any of my presentations before at Canada Green Building Council or HREI. So for the presentation today, I really wanted to talk a little bit more about the economics and operating cost side as we starting to see, increased costs of commodity price of natural gas and the carbon tax starting to come at increased rates. Starting in April this year, the tax is going to start going up by $15 per ton, where it'll be $170 per ton by 2023. So for the agenda today, I'll just talk about air-to-water heat pumps, just a recap on the technology overview. I won't go into a lot of details with different applications, but just talk about initial sizing and design. So we'll do a recap on that. We'll talk about why air-to-water heat pumps as a decarbonization tool. We'll talk about some weather according to regional areas, just to provide a national perspective to this. And then really what I want to dive into is energy and carbon savings of just partial fuel switching by using this technology with either backup gas or electric boilers. I want to do a detailed operating cost comparison as well. And we're going to finish it off with a case study for a project that's ongoing that Mitsubishi Electric's working on for a retrofit of a chiller that was upgraded to an air-to-water heat pump where it was sized for cooling to kind of get whatever they get out of it in winter to offset natural gas usage, which will still provide some good benefits and keep the building warm and comfortable throughout the winter. So we'll jump right into it. So just on the technology side, air-to-water heat pump, reversible chiller, reversible heat pump. These are all kind of misnomers for the same thing. What we're going to talk about today is air-to-water heat pump. So this is very similar to a standard air-cooled chiller. And for anyone who's not familiar, an air-cooled chiller has a vapor compression refrigeration cycle in the machine. And it's essentially just moving heat from one location to another. So to provide chilled water to use to cool our building in fan coils or air handling units, in order to provide that chilled water, we need to reject heat from outside the building. So we're doing that through an integrated condenser coil in the machine that's acting as a condenser in that refrigeration circuit. A reversible heat pump is essentially that same refrigerant circuit. They're designed a little bit differently, but they will have a four-way reversing valve inside the machine to be able to switch the direction of the refrigerant flow. So essentially in heat pump mode, we're just swapping what heat exchangers are providing which function. So the indoor heat exchanger that's connected to the building in wintertime, that's now acting as a condenser. So we're rejecting heat. And we're doing that by absorbing heat from that integrated coil in the machine, which is acting as an evaporator. So just basic vapor compression refrigeration cycle. By putting in work into a compressor, we're moving heat from one location to another to provide hot water to our building in heating mode. And heat pump 101, the coefficient of performance is the main metric that describes the performance of our refrigeration cycle, COP for short, which is the ratio of the heat output from the machine divided by the power input. So any kind of heat pump really will have a COP typically above 2. They can have, depending on the conditions, much higher COPs, anywhere from 3 to 4 or 5, depending on the system type and of course the conditions. But this class of heat pump typically will have a minimum COP of 2. So if we're comparing that to a natural gas boiler that's operating at an efficiency of less than 100%, then from a pure energy point of view, that can make a lot of sense. And if we're comparing that to an electric boiler that always has a COP of 1, that makes a lot of sense because those are both electrical sources. So compared to an electric boiler, reversible heat pumps make a lot of sense because they're less costly to operate by a factor that's equal to the COP. and also will produce less carbon, even though we do have clean electricity in Ontario. So a typical two-pipe changeover system. So the typical example I always default to is typical condos. In a past life, I spent a lot of time working for a vertical stack fan coil manufacturer, so I'm familiar with these systems. But a two-pipe changeover system is a system where we'll typically have a heating boiler that we'll use in the wintertime, and we'll shut that off usually May 2 for a long weekend, and then we'll turn on our chiller and start cooling our building. So the important thing about a two-pipe system is we're only ever supplying either hot water to all the units in the building, or we're supplying only chilled water to all the units in the building. If we have four-pipe systems, that's really just two-pipe systems stacked together, where one's in heating and one's in cooling, and that's available year-round. You could use these heat pumps in four-pipe systems, but we won't go into those details today. We'll just talk about simple two-pipe changeover systems. So if we have a typical two-pipe changeover system and we have a reversible heat pump that is a chiller, but it can also provide heating, then the idea with this type of equipment is let's use that and let's try to use it as much of the season as we can during the shoulder season and for milder days in winter in heating mode. We'll get into this in the next slide, but because the heat pump will have a fixed cutout temperature, in most climates in Canada, you'll almost always need an auxiliary boiler, but this can provide resiliency and redundancy for your building. So really it's about using the heat pump for as much of the time as possible and supplementing with a gas or electric backup boiler as required, and maybe just on those peak days. So basic design considerations, it's really a heat pump is influenced by the outside air temperature. So it's a little bit different than designing with typical boiler systems. So for any designers or contractors that are on the call today, if you are looking at offering this type of system for your clients, it's really important to understand at the start of the design process how that heat pump operates and behaves in the system, and design your system around the capabilities of that heat pump, whether it's retrofit or new construction. And there's kind of three key things that we want to watch out for on the heat pump. So we want to understand how the supply temperature from the machine is going to be affected by the ambient temperature, which is referred to as the operating envelope. And because we have a refrigeration cycle, as it gets colder, it's harder for the machine to extract heat. So our capacity will decrease. So we need to understand how that's going to reduce as it gets colder outside, and perhaps we can strategically select the sizing of the unit based off of supply temperature that we want to get as much BTUs out of the machine as we can. So along with the capacity reduction, we also have a coefficient of performance that will reduce, but again, the minimum COP of these machines, and we'll have examples coming up, is always above 2. So we'll go into the operating envelope here. So this example is based off Toronto, where we have a typical winter design temperature of about minus 23 degrees Celsius. So this operating envelope in yellow is showing us the maximum supply water temperature that the machine can supply for any given outside air temperature. So on the y-axis here, we have our heating supply temperature, and on our x-axis, we have our outside air temperature. And this is typical of what you'll find in the market from Mitsubishi or from other manufacturers making this type of equipment. We are starting to see a little bit better operating limits starting to come out with this technology as more manufacturers are investing in this type of technology, because they will be a very powerful tool for decarbonization and electrification of hydronic systems. So this is kind of comparable to what you'll find out in the market, but according to the operating envelope, or if you look at a manufacturer's brochure, it's also important to distinguish standard AHRI conditions versus application conditions. So if you look at our catalog, it'll say, hot water as high as 55 degrees Celsius, which is true. But whenever you look at the operating envelope, you'll see that the relationship between supply temperature versus outside air temperature will decrease actually below 3 degrees. So all the units in this class of heat pumps can typically give you around 50 degrees Celsius at about -5, and can typically give you about 45 degrees Celsius down at -10. But really at the fixed cutout temperature of -15, these type of machines do give you low temperature heat, maybe 35 or 40 degrees. With new A2L refrigerants, these will improve. So it's going to be interesting to see what technology is going to be out there over the next couple of years. But even working with this type of heat pump that gives you low grade heat at colder temperatures, there's as long as you design it properly in the system, you can still leverage that to ensure that you're taking full usability of the heat pump. So again, this is our design temperature for the city of Toronto, which is a requirement according to the building code. But whenever you look at the ASHRAE winter dry bulb heating design for 99.6, you'll see that it's actually minus 18.5, and even the 99% value is minus 15.7. So anyone dialing in from Toronto, it's been a pretty mild winter. We haven't, aside from the cold snap that we had over the Christmas break, we haven't really seen extreme cold temperatures, and it hasn't really been even below minus 10 for too much of the season. So, people often think that these heat pumps aren't really that useful to provide heat in the building because of the cutout temperature, but we'll see some weather data shortly here that will show how that's not the case for certain climates. So the second thing that will change according to ambient temperature is the heating capacity. So if we look on the y-axis here, we have our heating load and our heating capacity. So our heating load for the building is shown with this gray curve. So typically at the coldest temperature, that's where we have our peak load that's required. As it gets warmer, we have less heat losses from the building. So we have less than 100% load. This is an arbitrary curve, for example. It's going to be unique for every building type depending on the insulation and how the central plant's being operated. The blue line here is showing us the heat pump's heating capacity. So you'll see at warmer temperatures, this is where we have lots of capacity. So this line up here, number one, if we wanted to select a 140 kilowatt unit, that would allow us to meet our our design down to about minus 15, assuming that we're working with a 35 degrees supply temperature. However, in this example here, this is showing a bivalence point, which just means you're switching between two different sources, the heat pump and the boiler, at about minus 7. So this would be a system where you're happy with using about a 48, 49 degree supply temperature from the heat pump. So really the supply temperature that you're going to select when you're selecting a machine will kind of dictate the ambient temperature that you're using it down to. So usually 45C down to minus 10 is a good balance between having a broad range where you can hit that temperature consistently versus having a water temperature that's high enough to get good heat transfer through typical heat emitters. But again, depending on if it's a retrofit, we'll most likely in a retrofit scenario just size this based off the cooling requirement and whatever we get out of the machine and heating we get, and at what temperature do we want to deliver it, and that will kind of dictate to us our cutout temperature. But main point here is that you can downsize the selection of the heat pump by considering that, because even if we design our system for our worst case design scenario, we really only see that for 1% of the time. So a lot of systems are oversized in terms of how they typically operate in normal circumstances. So the last thing that will change is the COP, or the coefficient of performance. So on the left-hand side of the axis, we have bin hours. So and on the x-axis, we have our outside air temperature. So there's 8,760 hours throughout the year. So a bin hour distribution is just showing us how many hours do we spend at 0 degrees, how many hours do we spend around -1, and so forth. So yes, our design temperature in Toronto for the building codes around -23, but you'll see these extreme cold days, we do have a relatively low frequency. So really most applications for these types of heat pumps, you'll use it down as cold as -10, maybe -5, but and you'll use it maybe as high as about 10 into the shoulder season. So, but even between -10 and +10 for Toronto, we spend over 50% of the year within -10 and +10. So I always refer to that as good heat pump weather. And even if you look at a climate like Calgary, they still spend about 49% of the year between -10 and +10. So when it comes to using these heat pumps, it's not all or nothing. We just need to use the heat pump when that makes sense and use auxiliary gas when that's required to run. So the second thing that this chart is showing us is it's showing us our COP according to ambient temperatures for different supply water temperatures. So the key point here is this is also kind of telling us our operating envelope. So we looked at the operating envelope before, saying these machines could give you 55C. And you see that comparatively, this is the lower COP. So we're at about 2.5, but it's also starting at 3 and ending at 10. So that's kind of telling us our operating limits. So by choosing a lower design temperature, we can keep the heat pump running for more of the time and also increase the efficiency. So if we look at an arbitrary point of 0 degree ambient on a milder day like it is was yesterday in Toronto. Today's about -6. But if we're designing with a 45 supply temperature, our COP is 2.8, so that's still pretty good. But if we're able to drop that down by 5 degrees Celsius, we can increase the efficiency by about 10%, have a COP of 3.1. Or if we're designing with 35 degrees, we can have a 20% improvement and have a COP of 3.5, which makes a lot of sense if we're comparing that to an electric boiler. So just one point on this, if you're doing design or if you're looking at different systems, usually to use a lower water temperature, that will require different types of heat emitters, maybe more expensive heat emitters designed specifically for low temperature applications like low temperature panels. So don't discount it too soon. You need to look at the operating costs and the increase of efficiency that you'll get with a lower temperature. Not only that, but you're also going to be able to use this all the time down to -15, which is going to cover 99% of the operating hours. But the operating expenses savings, I should say, should actually counteract maybe the additional first cost of heat emitters. So we need to look at it holistically whenever we're trying to do decarbonization and electrification. We can't just take all the gas boilers in the world and change them to electric boilers and call it a day. That's not a scalable solution. So air to water heat pumps will have a part to play, and partial fuel switching is one of the good applications where even using it down to -5, you can still get good efficiencies, above 2.5 or so, 2.7. So generally speaking, with two pipe changeover systems, you'll select the amount of units that you need to meet your cooling or heating capacity. So again, most applications, because you'll need an auxiliary boiler, I'd recommend that you size these based off the cooling capacity, whatever you get out of the machines and heating you get, and then supplement the rest with auxiliary boiler, either when it's too cold for the heat pumps to run, or depending on the total capacity that's available from the heat pumps, you might need to supplement that with a backup boiler. You could add more heat pumps to meet more of the heating load in winter if you wanted to. It really just comes down to a capital cost. If you only need to run 3 units in summer for cooling, but you need 5 units in heating for winter, is the building owner going to buy an extra 2 units just to meet a little bit more capacity in winter? Or are they going to take the sizing chart that we saw right here into account and say, well, we're only going to use it down to a certain temperature anyway, so we'll have adequate capacity and supplement the rest with a boiler. So that's how we need to think about it. So now I just want to talk about air to water heat pumps, why you would choose those, and how they're a tool for decarbonization. And then we'll also get into some weather data and then some energy analysis stuff. So I've updated this based off TAF's 2021 report for Ontario's emissions. So unfortunately, the emissions for our electricity are going up. From the report I had from about, I think it was the 2019 report, it was about 30 grams of CO2 per kilowatt hour. 2022's estimated numbers coming in at about 43 grams, but the estimate for 2023 is about 70 grams. So I used to show this slide on presentations based on 31 grams of CO2 emitted per electrical kilowatt hour produced. And the savings used to be a minimum of 12 to 24 times, but now if our emission factor is doubling for the estimated value based off TAF, now that number is kind of being half to 6. But if we compare the electricity emissions with the natural gas emissions and we normalize it to the heat pump COP curve that we saw earlier, we can compare how many times more emissions are associated with an electric boiler or natural gas producing the same amount of heat. So our electric boiler is about 2 to 4 times more emissions and 2 to 4 times more to operate. This is essentially our COP curve because our heat pump has a COP curve and our electric boiler always has a COP of 1. So again, this is normalized to the emissions of the heat pump. And if we compare the heat pump to a boiler, even at -10, where the heat pump has its lowest COP around 2.1, natural gas boiler will still emit 6 times more emissions to produce that same amount of heat. And on milder winter days, that number can be as high as 10 nowadays. But we know that we're going to continue to see more renewable electricity added to the grid. So of course, this is going to fluctuate forever, but I did want to just have the updated numbers here. as part of this based off TAF's 2021 report. So again, I was alluding to weather data before. So depending on the application and the supply temperature that you're going to use in your system, that will kind of dictate how you're going to size your heat pumps. But what I like to show is, the total amount of time we spend below that imaginary cutout temperature. So if you had a medium to high temperature application where you do need a lot of high temperature hot water that's required, usually I recommend, try to design for about a -5 degrees Celsius cutout, because these machines can typically give you about 48 to 50 degrees Celsius here. And really, we still spend 47% of the year between -5 and +10 for Toronto. And times below -5, we spend about 682 hours. So roughly 3 weeks of the year. But again, that doesn't happen 3 weeks consecutively. Typically it's, cold snap for a day or two, or a few colder temperatures throughout the night that we'll see. So again, it's about using the heat pump where you can get good efficiencies and good supply temperatures within this range, and then auxiliary boiler operating below that. If we're able to design maybe with lower temperature water, 45 degrees, we can achieve that down to -10 typically, and times below -10, we're now talking about 200 hours, or 2.3% of the year. And if you're looking at a low temperature water application, so low temperature heat emitters, perhaps cascade systems where you have a central plant reversible heat pump supplying very low grade hot water to be an input to the evaporator side of another heat pump, either a large scale central heat pump or in-suite water source heat pumps that transfer energy to the air. There are different applications, and radiant inflow, of course, as well. So if you are able to design with a 35-degree temperature, we're basically covering off 99.5% of the year and running auxiliary below -15 for about 44 hours. So this is actually the weather data I've been collecting for the last 4 years now. So this is the average amount of time that's spent over the last 4 years. If we get outside of Toronto, because Toronto's not the center of the universe, and we look at Canada, we have a very diverse climate. Obviously the West Coast, Victoria, Vancouver, those are good heat pump markets, and they're doing new builds, high rise, with air to water heat pumps on the roof instead of boilers. And they can actually design these systems to eliminate the boiler altogether with their aggressive regulatory approach to banning natural gas in new buildings. That will start to escalate more for larger buildings over the next couple of years. Vancouver and Victoria are mature heat pump markets, but even if you get out into interior BC and places like Kelowna, that's where we see temperatures comparable to Toronto. The prairies is obviously a different story. Design temperatures below -30. Toronto and London are pretty mild, about -18 or so. Quebec gets a little bit colder. Montreal is about -23. And Atlantic Canada is a bit warmer because they're by the water. Same idea as the West Coast. So we do have a diverse climate, but what I did want to show is just breaking down the similar weather data for Toronto. So this is kind of sorted from best case to worst case. If we say, okay, well, a 45-degree Celsius supply temperature down to -10 is, if that's suitable for your buildings, just looking at, even Montreal, they spend about 300 more hours than Toronto does. So there's still good usability of the heat pump that we can get. Or if you say, we need a bit of a higher temperature for our existing system, -5 is maybe a more suitable cutout. We do see a little bit more time that's spent below -5, but sorry, I should have had the summary between -10 to +10 and -5 to +10, but it's pretty close to 40 to 50% of the time we spend in that good heat pump weather I was mentioning earlier. So it still makes a lot of sense even in different climates. Saskatoon, maybe the economics aren't as attractive, but for the milder climates like the West Coast, East Coast, and places like Toronto, it is much more economically attractive that we'll see coming up here as well. So just to summarize briefly about different applications, if we want to use these air to water heat pumps for low temperature applications, water loop heat pumps is a really good application that's shown here on the right. So these are common in condos in Toronto where we have compressorized units inside. So this is one way that we can provide 4-pipe comfort, still with 2 pipes distribution, and individual suites can be in heating mode or cooling mode. So typically the best way to do this system would be geothermal. But when geothermal is not feasible or it's too expensive, typically these systems will go cooling tower boiler. So we have a cooling tower to reject heat from the loop on the warmer days in summer. And on the colder days in winter, we have a boiler to inject heat into the system. During about +10 to +20 in the shoulder season, we don't necessarily need to add heat or reject heat from the system, because you could have some units that are in heating and others are in cooling. So you're actually going to exchange heat through the water loop, depending on the piping configuration, of course. So this is a really good application for air-to-water heat pumps because it lets you use it all the way down to -15 and cover off a significant majority of the hours throughout the year. But also, you don't even need to supply 35 degrees in these systems. You can supply 30 degrees, maybe even lower. So the lower temperature, the more efficient the machine will run as well. So that's something to leverage as part of the design process. Radiant in-floor heating is another good one. Domestic hot water preheat, ventilation preheat as well. If you can work with 35-degree supply temperature, you can do preheating of your ventilation air and then top it up on the air side with a backup furnace. And snow melting is another good application. Medium temperature, if you do need a bit warmer temperature, you're talking about fan coils, cabinet heaters, coils and air handling units. And for retrofits, it's one thing if you're retrofitting a building to lower temperature and you have 200 fan coils in the building that need to be changed. That's obviously very intrusive. If you are talking about just air handling units that you're supplying heat to, it's much more economical to just change a coil designed around the heat pump parameters in an air handling unit. To pair that with the heat pump, that's a bit more feasible and more realistic from a financial point of view. So really, when it comes to applications, you just want to find the lowest temperature water possible, because that's going to maintain the higher efficiency from the heat pump. And really, the objective is just ensuring that you're going to be able to run that heat pump for the most amount of time as possible, because that will lead to more savings long term. So just to compare energy and carbon emissions of different systems, if we look at hydronic systems, if we want to keep doing hydronic systems, but we want to decarbonize them, essentially our only other choices are electric boilers, which always have a COP of 1, or an air-to-water heat pump that has a COP anywhere from 2 to 4 or more. The air-to-water heat pump, though, is influenced by ambient temperature, where the electric boiler is not. But if we compare this to natural gas boiler, our COP is always less than 1. If we have a condensing boiler and we actually have cold return temperatures coming back and we're actually condensing, we can get efficiencies as high as 95 to 98%. But if we look at all three of these devices, we have the same thermal output, just provided from different sources. So we're going to compare those. So if you did want to just take a natural gas boiler and change it out to an electric boiler, we could certainly do that. But I think there's drawbacks to that. A lot of buildings won't have enough capacity to do that in the first place, so you might need to upgrade your service. You're fixed now to a COP of 1. You're going to have much higher peak electrical demand charges by having that inrush current every time the boiler turns on. And if your project requires backup generator for the heat source, then now you need to oversize your generator to have enough power to produce electricity to run an electric boiler at a COP of 1. But ultimately, I think we can't just change every gas boiler to an electric boiler and call it a day. We've achieved net zero. A lot of buildings don't have power to support shifting all the BTUs to electric, and it can't be done at scale, really. With the amount of electric cars that we have to put onto the grid, plus decarbonizing and electrifying a lot of buildings, there's just simply not enough distribution or enough power to actually just do this at a COP of 1. So we do need the heat pump to leverage the COP from the heat pump. But if your project requires that, we're going all electric now and we're going to make the investment now, that's great. You can certainly do that. You're going to leverage the heat pump, run that for a majority of the year, and use the backup electric boiler. But really, this is fixing your building to electricity from both your primary heat source and your supplemental electric boiler. So I think there's some advantages to be thought of for natural gas. I know everyone's in the market's trying to kind of get away from it with electrification, but if we consider the weather data that we looked at before, and considering that natural gas, we're going to use that for a much lower amount of time, that can still have some benefits. Maybe we're not getting that label of net zero on the project, but it's still providing some significant advantages, but also flexibility. This allows building owners to choose to operate based off lowest carbon footprint or lowest operating costs as well, by having that diversification in the system of an electric heat source and fossil fuel source as well. So this is an arbitrary example just to kind of illustrate not only the carbon, but just the kilowatt hour savings for whenever we're just designing new buildings and trying to meet our energy codes. So this is an example based off Toronto bin hour weather data. And what we're going to look at is two different scenarios. So we're going to look at if we're using kind of that medium temperature of 45 Celsius, which would have a cutout of -10. We're going to look at using two heat pumps that's basically serving the system in this green triangle here. And if we say 45 is a little bit too cold, 50 degrees is more reasonable to provide heating, we're also going to analyze that where we selected the same units, but rated them down to -5, which are giving 230 kilowatts at this value to meet this peak load. And then we're going to compare that to the big red triangle here, which is just an all gas or an all electric system. And then we're going to compare the ratings. So this is actually taking into account the part load operation of the heat pumps, and it's taking into account as well the decreased COP by having 40% glycol in the system, which is a typical requirement that we'll talk about later. So still have a COP in this scenario of about 2.1 or 2.07, depending on the temperature. So if we just look at that -10 example, so here we're going to compare using electric heat pump within this green triangle here down to -10, covering off these bin hours. And for the low frequency of hours that we have here, we're going to compare that to using a backup electric or backup gas, or all electric and all gas for the big triangle. So if we look at the worst case of all gas in that system, all these bin hours being served by a gas boiler would have approximately 1 million kilowatt hours of energy when you convert cubic meters of natural gas to kilowatt hours. And if we look at a electric boiler, we have a little bit less, about 880,000 kilowatt hours. And that's just due to the difference of efficiency, because our electric boiler has a COP of 1 and our gas boiler has a COP of about 9.95. In these two scenarios, the green is showing us air-to-water heat pump being used to shift a lot of these hours to heat pump, and then backup electric for yellow. So that's about 388,000 kilowatt hours. Or if we use air-to-water heat pump and a backup gas boiler, we're at about 400,000 kilowatt hours. Now, this is just a high-level bin hour analysis, so this doesn't take into account the staging of the heat pumps when the units are going in defrost. This is really just intended to provide the relative comparison whenever you're comparing it, just for the total amount of energy based off the bin hour distribution. But even if we compare that to a gas system, to air-to-water heat pump with supplemental gas, we can have a significant reduction of our total energy used. Similarly, with the -5 example, we're maybe going to use the heat pump down to -5 only, and then use a little bit more gas, because we do have a little bit more hours here between -5 and -10. But even comparing that same example, our gas is still fixed the same it was in the last example, and our air-to-water heat pump, we're just using a little bit more natural gas. So instead of 400,000, we're using about 516,000 kilowatt hours, but still a significant reduction just on a pure kilowatt hour, and which is required as part of the design process for energy use intensity designs for buildings. So there's some significant kilowatt hour savings that can be realized, and the heat pumps can be leveraged as part of the design. But how does this look on the carbon side? So if we look at emissions from natural gas boiler to electric boiler to air-to-water heat pump with backup gas or electric, our worst case with the most emissions is obviously the scenario where we have only natural gas that's being used. Electric boiler would have significant reduction, but that's perhaps not feasible in all scenarios. But all the combinations of air-to-water heat pump, regardless of the cutout temperature, and the backup heat source, gas or electric, still has a substantial reduction of total carbon emissions that can be used. So even looking at the heat pump down to -10 would offset about 166 tons per year based off this load profile. The load profile will kind of dictate what the results will be, or even at -5, even though you might think, well, our heat pump's not meeting our full design temperature, well, it doesn't really need to, because you can still see some significant savings, carbon savings, kilowatt hour savings, and cost savings that we'll get into shortly, even by using it down to -5 of about 140 tons offset per year. So I just want to go into the operating side of it, and then we'll talk about case study. So if we want to compare operating costs for natural gas supplying the same amount of heat, it's the same amount of heat provided to the building, whether it's provided from the heat pump or natural gas boiler. So how do we compare the energy sources? So if this is the same amount of heat provided from either the boiler or from the heat pump, if we look at our boiler and we take our total delivered natural gas prices, and we take our dollars per kilowatt hour delivered of natural gas and divide it by the boiler efficiency, that's telling us how much money we're spending to provide this 1 unit of heat. And we do the same for the heat pump. We take our delivered cost for electricity, and we do dollars per kilowatt hour electricity and divide it by the COP. That's how much money we're spending for the same amount of heat. We can essentially rearrange this equation and figure out what break-even COP do we need in order to be cost neutral based off the ratio of cost between electricity and natural gas, and express it like this. And when we plot this equation, so it's pre-plotted here for different efficiencies, so 95% in black, as low as 80% here in red. So what we do is we figure out what our price ratio is, and I'm on the condo board for my building, and I've been looking closely at our utility bills over the last couple of years. And in December of 2022, our average delivered rate for natural gas was about 50 cents, and our average delivered electricity price was about 13 cents. So I'm using 14 cents here to be a little bit more conservative. So essentially, you figure out what your cost ratio is when you convert these into kilowatt hours. So 2023 cost ratio is about 2.815. So on this chart, you basically draw a horizontal line on the y-axis here for the price ratio, and wherever it intersects with whatever boiler efficiency you're comparing it to, you basically draw a line down, and that tells you the break-even COP. So if we're comparing this to a 95% efficient boiler, we would need a COP of 2.67. If we're comparing it to an 80% boiler, our break-even COP that we need is about 2.25. And again, this doesn't only apply to hydronic heat pumps. This applies to furnaces. This is just a pure energy comparison based off the costs. So really useful when you're just looking for a quick rule of thumb to figure out if a particular heat pump application makes sense. So as we know, we're seeing increases in the carbon tax pricing. So in April of this year, we're going to start to see the price going up by $15 per ton. So under the previous scheme from 2019 to 2022, that had the tax going up by about by $10 per year. From 2023 to 2030, that's going to increase to $15 per year increase. And if you look at the carbon tax portion for the bill, essentially with a $10 increase to the tax, it translated into pretty much 2 cents year over year into just the tax portion. So we're not really considering commodity cost. So that means a $15 tax increase will translate into 3 cents year over year. So between 2023 and 20 for the carbon tax portion, and that's going to be 24 cents added to the price by 2030, on top of whatever changes plus or minus we see for commodity costs. So just kind of forecasting this using today's rate of electricity of about 14 cents, I'm applying here 2% inflation year over year for electricity prices. Natural gas, 2022 at 50 cents, 2023, 53 cents, and then adding that 3 cents year over year just for the carbon tax portion. And this chart here is showing us our COP curves that we were looking at before, but we've also put here a horizontal line showing the break-even COP. So if we're designing, for example, a system with a 50-degree supply temperature based off these rates today, that would be economical. It would save you more money whenever the heat pump curve is above this line. So in this example, at 50 degrees C, this is economical. It's actually saving you money down to about -3. And then below -3, we might be spending a little bit more money to run the heat pump, but we need to look at it through the average of the year. and look at the average, and it should balance out. But what I want to illustrate here is that over time, between 2023 to 2030, as just we apply the carbon tax portion and a little bit of inflation for electricity, the minimum COP that we need to be cost neutral keeps getting lower and lower. So if we look to 2030, even if we're using a 50-degree supply temperature again, our COP is above the 2030 break-even line. So it's always going to be more economical to operate. So this is the trend where everything's going. So especially for new construction projects, if you're selecting technology, you know that building's not going to go up for 3 to 6 years, depending on the size of the building. So it makes a lot of sense to look at the long-term forecasts of this, because it's not going to be commissioned for a number of years after the selection process. So I mentioned earlier, I was on my condo board and I've been collecting data, and I did want to share this because it is just eye-opening seeing how much the rates have been going up. So this is just the data for January of 2022. So at the start of January 2022, our average delivered pre-tax amount for natural gas was about 32 cents per cubic meter. We saw a commodity cost increase in June and a carbon tax increase in April. Actually, I think there was 2 price increases from Enbridge last year, but based off December, the average delivered rate per cubic meter was about 49 cents. If anyone's looking at utility bills, the federal carbon charge is a line item in most jurisdictions now where it's being collected. So essentially, before the steep increase to the commodity cost, carbon tax represented about 25% of the pre-tax bill was just going to carbon tax to the federal government. Now it's about 20% because of the high increase of the commodity cost. So now you're still collecting at the same rate for carbon tax, but the total got bigger, so your percentage goes down, but that's still 20% of it. On the electricity side, average electricity has been about 13 cents delivered. And this does not include the Ontario energy rebate. So I'm just being a little bit conservative here. If you add the Ontario electricity rebate on top of that, that's another 11%. So basically comes out a wash for paying the HST on it. But what I want to illustrate here is the electricity to natural gas ratio of how it has basically how the cost of natural gas with that increasing is becoming more favorable for heat pumps. And again, we're comparing this to a 95% efficient fossil fuel system. If we're comparing it to 90 or 85, it's even more attractive. But just to look at the summary of 2020 carbon tax and from 2020 to 2022, 2020, we were spending about $105,000 per year. And with carbon tax in its infancy, we were spending about $21,000 of this was just going to carbon tax. 2022, with the increased carbon tax, increased commodity cost, we spent last year $172,000 with about $38,000 of that just going to carbon tax. So obviously, doing something about your emissions and doing even partial electrification can still have some advantages in the short term and in the long term for lowering your operating costs. Last thing on this that I wanted to show that I find is interesting is just that break-even COP. Obviously, your rates fluctuate. You know, whenever you have less usage in the summer, your natural gas pricing is higher. But this red line at the top is the 2020 rates, and 2022 is the break-even COP that's needed based off the 2022 rates. So over time, we're seeing this break-even COP that you need from a heat pump getting lower and lower. And as of December of 2022, that break-even COP was 2.65. So it's good for heat pumps, and we're going to continue to see this trend as well as the carbon tax starts to come in more aggressively, and as we who knows what will happen to the commodity costs for natural gas. I don't have a crystal ball, but generally things these days are going up, so it's important to keep this in mind. So again, you can watch the YouTube video later for the equations and things like that to make your own analysis and to do your own analysis on the bills. I would just say look at your total of the bill for cubic meters, total cubic meters, and the total pre-tax dollar amount, and divide the two, because you do need to account for all the distribution charges, because you'll see that the rate's actually much higher than whatever your commodity cost itself of that unit of gas is. The delivery is almost the same amount as the cost of the natural gas. And you have to do the same thing for electricity. And I would also like to point out that all these economical analyses that I've been providing here doesn't account for demand charges from the heat pump of having that peak inrush current. So that is a kind of qualifying statement on that. That's not accounted for in these analyses. So last thing on the agenda for today, just going to talk about a retrofit scenario. So I'll try to wrap up here in the next 5 to 10 minutes and have a couple minutes for questions. So we did a heat pump project downtown Toronto at a building called the French Quarter Shared Condo Facility. It's actually 2 condo buildings at Richmond and Jarvis Street. It's a shared condo with 2 towers, common parking garage. So we've been working with the owners of that building, and we've assembled quite a great project team. For Service Residential's property manager, and they have in-house energy people who have been really supporting the condo board and driving this. So I think it's fantastic the work that they're doing. The consulting engineer was Remy Consulting Engineer and was installed by Prestige Mechanical. And on the regulatory side, we did have some support from TAF and the Toronto Regional Conservation Authority through the Sustainable Technologies Evaluation Program, STEP. So both TAF and TRCA were quite interested in doing a detailed case study on this with some monitoring to monitor the efficacy of the heat pumps in this type of scenario. So we had a great project team and looking forward to the long-term monitoring. The equipment's just been starting to be commissioned. So certainly in future webinars, we'll have more real-time operating data to kind of report on how the system's performing. But essentially they had an air-cooled chiller that needed to be replaced, and the condo board was forward thinking, and instead of replacing it like for like, that's a fixed asset where there's no rate of return. But with the heat pump sized for cooling, they can get as much heat out of the machine in the winter when it makes sense to do so, whenever they would normally shut off that chiller. So their existing chiller was kind of in a small enclosure on the penthouse, and this was a 110-ton chiller. So it's typical 2-pipe changeover system for Toronto with just diverting valves for summer and winter mode. So chilled water in the summer, boilers in the winter. Just water throughout this whole system. With the heat pump retrofit, due to the sizes and physical size of their existing chiller, we actually had to split it up into 2 units. So there's a 55-ton nominal heat pump. So essentially half the cooling capacity of the original unit is fitting into the same space. So that is one thing with heat pumps. They are larger than typical chillers. That's because to extract heat at -10 or -15 ambient temperature, they need a lot of surface area on the coils for the refrigeration circuit in order to actually pull in that heat. So they are larger. So we had to make room on the upper roof for the second unit to be placed, and just have a photo here from crane day. So what's also different about this system is the way the boilers were put in and how the heat pumps were put in. So heat pumps, unlike a typical chiller, they're not drained in the wintertime. Heat pumps will need glycol in them, because if the heat pump's going to work down to -5, it could be in a thermal off state, so that water is exposed to, of course it's insulated, but that's not going to protect it from freezing. So you need glycol in the system. The second thing with heat pumps is you do need buffer tanks to prevent the compressors from short cycling. So the way this was configured in the building was with heat exchangers to decouple glycol from the entire building. They didn't want to have glycol running through the building, just the cost of filling up that system with glycol plus the cost of operating pumps with higher energy consumption. So they interface that with heat exchangers. So essentially the main building loop comes back, and then based off the building automation, they're basically at the heat pumps dumping heat into the building loop, going to the fan coil system. This system's going to operate just on a simple changeover. So they're going to, at first this was designed for 116 kilowatts and 155 kilowatts at -10, still with decent COPs. And, if in the vertical stack fan coil system, if they get complaints from residents that, there's not adequate heating, they're going to kind of dial back that cutout temperature to have a higher supply temperature. to maintain indoor thermal comfort, which is the most important thing. And secondary to that, we want to fuel switch as much as possible. So they're a little bit different, and the system did require reconfiguration. So they actually had, there's an existing boiler behind here that got demoed, and they had to make space for the new pumps, new heat exchangers, and so forth. So it's an interesting project, and we'll certainly report more. But for today, just on the economic side, I wanted to just provide a quick summary on the economics. So if we look at a like for like, and this is again per the reserve fund study, where there's essentially an allowance for certain capital costs throughout the life cycle of certain equipment that's planned. So in the reserve fund study for air-cooled chiller replacement, including labor, it was about $300,000 allocated for that. Heating boilers, there was $80,000 allocated for that. And that was included in this because the heat pump will act as a boiler to a certain extent. So that was included from the condo corporation's point of view. And they also had a line item for mechanical control system, which was required to control the heat pumps, control the staging, and control the auxiliary boiler, and to tell who to do what at any given moment in time. So if they were just going to do like for like, maybe put in a new mechanical control system, it would have been a budget of about $400,000. Based off the reversible heat pump with equipment, plus all the installation, engineering fees, and so forth, total project budget was about $600,000. So what we look at is, the requirement for this project is they needed a chiller. So here they just really got a chiller plus. So we look at the incremental cost, because what additional money did they pay to get that heating functionality out of that system? So the incremental cost, if we don't consider incentives, was about $206,000. There was about close to $50,000 of incentives from the different partners on the project, including Enbridge as well, and IESO rebates. So if we account for those incentives, it was about $160,000. I think over time, though, we'll see a lot more funding become available and more incentives as the federal government and provincial governments need to drive electrification. So I think we're going to see more incentives coming in. So we look at an incremental cost of about $160,000. So if we look at just the carbon tax and based off 85 tons of CO2 offset per year, in 2023, it's about $5,500, but by 2030, when carbon tax is at $170 per ton, it's about $14,000 savings. But if we look at the cumulative savings, it's $200,000 over a 15-year life cycle. This doesn't include gains of efficiency on the chiller side as well. So replacing a chiller that's 20 years old with today's high efficiency chiller that meets ASHRAE 90.1 will have some good benefits. And also with the current control scheme that we talked about, we're certainly going to look to optimizing that in the future to have the heat pump running for more of the time, because the more of the time the heat pump can run, the more gas we can offset and the more savings that can be realized. So that's going to be an ongoing thing, I imagine, over the next couple of years of trying to push the boundaries year over year and collecting data to see what's making sense or not. But with incentives, it's not a typical 5-year payback, but what I'm trying to illustrate here is that it's within the realm of possibility. It's not, a couple of years ago when utility costs for natural gas was very low cost, people would tell me I'm out to lunch. But I think over the last year, even as things have transitioned, it makes the business case a lot more attractive. So you might also be thinking that, what about the operating cost, because you have to buy electricity? So originally, when we were working on this project, we actually provided an estimate taking into account our similar bin hour analysis with a load profile from the building, which is taking into account the heat pump's efficiency at different points and comparing that to a boiler. It's important to have an accurate load profile, because if the load profile is overestimated, then the savings will be overestimated. So for the previous example, where I'm just showing it on the carbon tax, I didn't compare these same ratings of 86 tons because I need to know how much electricity has been added. Because once the savings were submitted to Enbridge, they looked at the billing data and thought it was overestimated, and they came in with a lower number of about 45,000. Our original estimate was about 80,000 cubic meters per year. and adding 248,000. But I did want to just show the original because it's fuel switching based off bin hours. So the proportion of the two is still important. So you can consider that this is scalable. So even if we look at utility rates of 14 cents for electricity, 2% year-over-year inflation, and natural gas 53 cents for 2023, and then adding those 3 cents until 2030, we still have cumulative savings that will pay for it within a 15-year. And again, typical life cycle of this equipment's 15 to 20 years, depending on maintenance and conditions, of course. But within the life cycle of the machine, the savings can be realized to kind of pay for that investment in decarbonizing your building. And now you have, once that machine's at end of life, you can replace it with a new reversible heat pump that will work well. So anyway, finishing off just in the nick of time here. So I appreciate everyone coming in, and we can stay on for questions now if anyone has any questions. And I'll just
Awesome. Fantastic.
pop up my contact information here.
There you go. Look at that nice picture. I got two questions for you. In the presentation, you show the boiler and chiller in parallel. Can they be used in series and run both systems at the same time, or do you turn off the chiller to be more economically effective?
Turn off the heat pump. Yeah, I get this question a lot. I anticipated this. So really the key for a heat pump to deliver heat to the building isn't really the outside air temperature. Well, it is, but it's also the return temperature from the system. So if this is our operating limit, and if we pretend we have typical condensing boiler design of 140F, 120F with a 20F delta, this is the design delta T that we're going to see on our design day. So Toronto, it'll be minus 23. We have less heat losses as it gets warmer. So our return temperature is basically always going to be above this line. So if you did want to say, okay, well, let's do series heating. Let's have the heat pump bump it up by 5 degrees and then have the boiler bump it up the other 5 degrees. That's fine whenever it's, between 3 and 10. But what happens later tonight whenever it's minus 10? If your return temperature is 50 degrees or higher, maybe it's here, the heat pump's going to say, well, you're telling me to make 45-degree water, but it's 52 degrees. I've done my job, and the heat pump will actually never run. In reality, your boiler's on a reset curve, something like this, so it'll kind of work down to the lower end. So it's important to design your systems to have the lowest return temperature possible to get the heat pump to return more. And if you have any questions, feel free to reach out to me.
Yeah, you've got the contact information there. Maybe one more before we go here. Did the new design with heat pumps produce the required outlet temperatures to meet the building's existing design temperature?
That depends on what the building's existing design temperature is. If you're comparing it to a baseboard radiator system at 100 degrees Fahrenheit, which is 80 degrees Celsius, there's no heat pump on the market that will do that. If you're aware of it, please tell me. One way you can do it is with cascades. So I was talking about those water loop heat pumps in suites. There's also large water-to-water heat pumps. And sometimes those are used for domestic hot water in geothermal. So you can actually have the air-to-water heat pump working outside down to minus 15, supplying low-grade heat at high efficiencies to the water-to-water heat pump, and that can boost it up to really high temperatures on the secondary. That's if you just want to match nameplate for nameplate with your boiler. I think, though, we need to take a little bit of a holistic approach, and because you're just trying to match the heat loss of the building. So if our building and this project downtown, I was at the building yesterday, and the distribution to the building was 40 degrees Celsius, so about 100 degrees Fahrenheit, and it was still outputting comfortable air from the fan coil unit. So I appreciate the question, but I think we also need to get more towards a holistic view of things, of saying, well, our heat pump just needs to supply heat down to minus 5 at good efficiencies and high enough supply temperatures, and then just use backup gas below that.
Excellent. I'm getting alarms saying get off the webinar here. So thank
Yeah,
you so much, Chris.
thank you.
Another fantastic presentation. Hope you can join us again.
Yeah,
Something on this
absolutely.
topic.
Sure.
And yeah, if you'd like to watch this, please go to HREI's YouTube, reach out to Chris at the contact provided. And yeah, thank you so much, everyone, for joining us. And Chris.
All right, ciao. Thank you.
Take it easy. Cheers.
All right, bye.